All right. In this video, we're going to look at how to count a number of distinguishable permutations, which means you're looking at the several items where some of them are the same as each other and thinking how many different ways can you arrange them so that you can tell the difference, right? So I've got up here 6 of these red stars, these 8-pointed stars, 5 of these blue 4-pointed stars, and 3 of these black triangles. And, one arrangement would just be, we just put them in order like that. The 3 black triangles on the right end, the 5 blue stars, and then in front the 6 red stars. That's one of the many orders. And again, we say distinguishable because all in all, you've got several objects here, right? We've got 6 plus 5 plus 3 is 14 items. So, if you just think permutations, you might think like 14 factorial, right? You have 14 items. How many choices do you have for the first slot? 14. And then for the second slot, 13, and so on, right? The problem is, if you just do 14 factorial, then you're counting this current arrangement at the top there, the 6 red stars, the 5 blue stars, and the 3 black triangles. You're counting that as one permutation, and then if you switch the 2 red stars that I just switched, that would be another one. And every exchanging of the order of indistinguishable items would still count separately in your 14 factorial figure. So that doesn't tell the whole story. But that is a good starting point. And if we had a little marking on each one of those objects, then that would be right? Like if this was like red star 1, red star 2, like if there's a little number on each one to make them look unique, right? Sort of like a little barcode or something, right? Or maybe I wouldn't call that 7 and 8. Maybe this should be blue star number 1 through 5, right? If we had that, then the 14 factorial would tell the whole story, right? That would be right. However, we don't. And we want to count all the red stars the same and all the blue stars the same and the 3 black triangles the same as well. Let me just point out before we get into how to hone in on those distinguishable permutations, how to remove the indistinguishable repetitions. Before we hone in on that, let me point out what that 14 factorial is. So 14 factorial, let me use a better color there. 14 factorial is 14p14. How many ways can I do a permutation of 14 objects out of 14 objects? That's what that means. And the formula for permutations, NPR, and you saw this in the last video if you watched that, is n factorial over n minus r factorial. So in this case with 14p14, it would be 14 factorial over 14 minus 14 factorial. And if you're looking at that, scratching your head like, wait a minute, what's going on in the denominator there? You should know, it's important to know this for combinatorics in particular, that 0 factorial is 1. That's important if you're wondering why. Well, the best reason is that it kind of needs to be in order for combinatorics to work. So that when you take the number of ways that you can do a combination of 5 things out of 5 things, if you plug it into the formula, it doesn't work if that's 0, right? That's my best answer. We could dive more into that maybe another time, but for this video, we'll just leave it at that. 0 factorial is 1. That's important to know. Anyway, so 14p14 tells you how many ways you could order 14 different items. The problem is that in this case, we don't have 14 different items. In this case, we have 14 items, but 6 of them are one thing, and 5 of them are another thing, and 3 of them are another thing. And so what you need to do now is think, okay, once you pick one of these arrangements, right, once you pick, like the one I have up here, right? Or let's shift it around a little just to mix it up. Once you pick, that was a silly one to move. Once you pick one of these arrangements, maybe this arrangement right here, let's make it a little more interesting. The question is, how many times does that arrangement get counted in the 14 factorial? How many repetitions, how many duplications do we have, right? How many redundancies? And so what you need to realize is that within each shape, there's a bunch of repetitions, right? For example, I have 5 blue stars. 1, 2, 3, 4, 5. I had them numbered earlier, right? And what I could do is I could reorder those. I could switch 1 and 2. And if that's all I do, that's another one of these 14 factorial ways to do it. So the question is, how many different ways can I order those 5 blue stars, really, right? If we can do that, then we can take out all of the 5 blue star duplications that are in this 14 factorial. And so if you ask yourself, how many ways can I order these 5 blue stars? It becomes a much simpler problem, right? There are 5 blue stars. Whatever order, whatever organization we have, whatever solution, whatever distinguishable permutation, I guess is what I want to say, there are going to be 5 blue stars in it. And if you just focus on those and ignore everything else, 1, 2, 3, 4, 5, you have 5 slots now. And what do you have? You have 5 choices for the first slot, right? It could be star 1, 2, 3, 4, or 5. And then once you pick one, you have 4, and then 3, and then 2, and then 1. So it's really 5p5 or 5 factorial ways to arrange the 5 blue stars. And for each one of those 5 factorial equals 120 ways that you can arrange those 5 blue stars. For each one, we counted all of them in the 14 factorial, but we don't want to. They're all the same to us because we don't see those little green numbers on the blue stars. We just see the blue stars. And so because of that, what we really want to do is we want to divide that out. We want to divide out the 5 factorial to remove the repetitions from the blue stars. Okay, and we're going to do the same thing then with the red stars, right? How many red stars are there? 1, 2, 3, 4, 5, 6. They're indistinguishable. I could number those 1 to 6, and then I could distinguish them. Every single ordering of those 6 red stars, of which there are 6 factorial, right? Let me do that in the same color there. Well, no, let's leave it. I like that. In fact, let's make the 5 factorial blue to match the blue stars. Every single ordering of those 6 red stars is represented in the original 14 factorial. And there are 6 factorial ways to order the red blue stars, just like there were 5 factorial ways to order the 5 blue stars. I think I said red blue stars. The 6 red stars is what I meant to say. And so we need to divide all those out also. Those are all repetitions, right? And then we're going to do the same thing for the 3 black triangles. We're going to divide out a 3 factorial. And we just divide all of them out. Those things are all multiplied together on the bottom. In fact, you could kind of picture a gigantic, and it would be enormous, an enormous tree diagram representing all the different combinations of those repetitions, right? So how many different ways can you arrange the 3 black triangles? Well, you have 3 branches on that tree, right? You have 3 factorial. You have 6 branches on that tree, right? You could do triangle 1, triangle 2, triangle 3, triangle 1, triangle 3, triangle 2, triangle 2, triangle 1, 3, 2, 3, 1, and then 3, 1, 2, and then 3, 2, 1. Those are all the different orderings of the 3 black triangles. That was the easy one. Now, for the blue stars, there's 5 factorial different orderings. That's 120. So I would now need 120 blue branches in my tree diagram off of each one of these. I need 120 of those to show all of the different orderings of stars 1 through 5. So I would have like 1, 2, 3, 4, 5, 1, 2, 3, 5, 4. And, and so on and so on and so on for each of these. And then on each of those branches, I would need 6 factorial, which is 720 branches in red, coming off of all of those 120 times 6 branches in blue. And so it ends up, I think, being 720 squared, because 3 factorial is 6, which makes that like another 6 factorial. Anyway, it's a lot, right? There's a big number in that denominator. And those are all of the repetitions, because for every ordering you can do of the blue stars, you can also combine that with any one of the orderings for the red stars and any one of the orderings of the black triangles. And so those multiplied together are really the total number of like repetitions of distinguishable permutations, right? The number of times we repeat each distinguishable permutation if we just do 14 factorial. So that's really the formula. If you want to find the number of distinguishable permutations of n items, and you have x1 of item 1 and x2 of item 2, and so on, ... The formula that we're going to have is going to be n factorial over x1 factorial times x2 factorial times, until you get to x, I'll just say k factorial if there are k different items total. And that's it. It's a pretty simple formula to use, but that's why it works. Hopefully that makes sense. Let's look at one more example really quickly here. The word Mississippi. If you rearrange the letters in the word Mississippi, just make them all caps so we can't tell the difference between any of them. The question mark is not part of this question. And so it might be worthwhile to count each letter. We've got 4 S's. We've got 4 I's. We've got an M. And we've got 2 P's. I think I counted that right. What's that? 11 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks good to me. And so how many ways can you rearrange those that are different from each other? Well, there's 11 factorial ways to rearrange 11 letters. But within that, I have rearranged my S's, S1 through S4, and I've counted all those arrangements. There are 4 factorial of those arrangements. I have to divide that out. Same thing with the I's. I have to divide that out. You can put a 1 factorial in here for the M, but you don't need to because there's only one of them. And then 2 factorial for the P. And then while you're at it, you could even throw in a 0 factorial for the 0 Q's in the word Mississippi, and it won't affect the answer because remember, 0 factorial is 1. I just thought I'd throw that in there again. I didn't bother to actually compute these. I guess I could. I have a graphing calculator right here. And if we wanted Mississippi, let's do that one. I want to say alpha. Where's my, oh, no, that's not the right one. Function. Oh, there we go. Yeah. Factorial is choice 9 here. So let me get back out of here. I want a fraction. And I want 11 factorial on top. Choice 9. And then I need a 4 factorial, a couple of those. Another one. And a 2 factorial. I'm just going to put times 2 because 2 factorial is 2. And there are 34,650 different ways you can rearrange the letters of the word Mississippi and have them actually look different. 34,650. The numbers can get pretty big because you're dealing with big numbers when you have factorials. If you want to do something like this by hand, If you're taking a math competition and you're not allowed to use a calculator, you might think, hey, that's absurd. How could I do that by hand? They're not that bad, though. Factorials are actually kind of fun to work with by hand. What I would do on this, 11 times 10, 9, 8, I'd get down to 4, 7, 6, 5, and then I'd just do a 4 factorial. And then we got 4 factorial, 4 factorial, and 2 factorial, and then start canceling stuff. And you can cancel a lot typically. 4 factorial is 4 times 3 times 2. So if stuff doesn't match up quite right, I might just do 4 times 3 times 2, leave out the 1, and then you can reduce the 4 and the 2 with the 8, and then you can reduce that 3 and that 2 with the 6, and you end up with 11 times 10 times 9 times 7 times 5, which is a little less daunting. I'm not going to have you watch me multiply that out, but we could probably all get through that one without too much pain. Anyway, that's all there is to distinguishable permutations. It's kind of like when you're dividing out those factorials on the bottom, it's a lot like when you take permutations and you divide out the orders to make a combination, like we talked about in that last video, to go from the permutation formula to the combination formula. Here you just have to divide out more repetitions. So it's very much the same idea. Thank you.